Welcome, everyone. Welcome to our first public lecture in the second half of 2018. We assembled the new schedule, which is available outside the door, with the next 6 months of events, both for our public lecture series in stargazing, as well as Astronomy on Tap, which is, it's fun from the cheers in the audience. It's at a local bar. You can drink beer. Well, if you're of age, you can drink beer, although all ages are welcome to attend, and we have that okayed by the bar. And then we have a couple of informal talks about astronomy, much like this, but more alcohol. So, as you can see, it's still kind of daylight outside. So since we're so close to the summer solstice, the sun is setting quite late, but we have a lot of really great targets available this evening. So just as a layout of how this is going to go, we'll have a wonderful talk by Donal O'Sullivan in the next few minutes. It'll be about 30 minutes. Then we'll take questions for 5 minutes or so. Then there will be an intermission period where we set up our Q&A panel. And basically from 8:30, 8:40 until 10 o'clock, you guys are welcome to stick around in here and ask various questions about astronomy, space science, physics, what have you, of our expert panel consisting of postdocs and graduate students here who work on various different subject matters. As well as you can go outside, go out the front door, follow the signs, and the field directly adjacent to the astronomy department will have 3 telescopes. They're setting them up right now. Looking at the targets we have tonight are the first quarter moon, which is always fun to look at, Venus, Jupiter, Saturn, and Mars. Mars is nearly on its closest approach in several years, so it's very, very bright in the sky. I don't know if you guys have seen it in the sky. After about 9:30 or so, it's visible in a big, bright spot. You might have confused it with an airplane because it's so bright. So all those targets will be available to look at, and you're welcome to come in and out of here, ask a question, then run outside and look at a star or a planet. What other announcements? Oh, the only rules for the field are no littering, no food, no soda pop, no pets, no high heel shoes. Sorry, ladies. Because it can poke a hole in the astroturf, and then we don't get to use the field anymore. So if you have high heels or something of the sort, just take them off. The grass is comfortable. I think that's about it. So let me introduce our speaker for this evening. Our speaker is Donal O'Sullivan. He is a fifth-year graduate student here in the astrophysics department, and he did his undergraduate work at the National University in Ireland. And his research consists of doing lots of cool stuff that's related to my own, so I really love it. Galaxy evolution and understanding the nature of the gas around galaxies and in between galaxies, the circumgalactic medium and the intergalactic medium. But tonight, he has a special talk in store for us about diamonds in the sky. So please welcome Donal O'Sullivan.
People hear me? Okay, let me know if you can't hear me. So, thank you, Cameron, for having me here, and thank you, everybody, for being here. I'm really excited. So, as Cameron said, this isn't a topic that I actually work on in my research, but it's one that I really love telling this story. And essentially, it's, as you might have guessed from the title, it's about diamond white dwarfs, specifically a white dwarf called Lucy. Which you might guess if you're a Beatles fan what that means. And the reason I love telling this story, I won't do that again. The reason I love telling this story is that this whole talk essentially comes from this email that I got a few years ago, where it was from a middle school student who I had given my email out, and this middle school student emailed me. It was the only one in his class to do it, and he said, "Is the star Lucy made of diamonds?" And if you're not familiar with the topic, you kind of look at that and you think, okay, maybe. I was about to email him back and say, hey, thank you for the email. I think you might be confused about a Beatles song. But I figured, no, I'm a scientist, I'm a researcher, so I did what any good scientist would do. And that led me to this. And I was like, oh, okay, actually, There is a diamond Lucy of some kind, and it turns out it's a white dwarf. It turns out the whole reason it's called diamond is something to do with crystals, something about the core. And so I got really interested in this. And one of the fascinating things about being here and living here is you have experts that you can just walk up the stairs and talk to. So I talked to Sturl Finney, who's an expert in this kind of stuff, and he got really excited and told me all about it. And so I learned about this thanks to that email. So that's what I want to tell you about today, and hopefully you can go through the same process I did about learning about what does that question really mean. Is the star Lucy made of diamonds? Well, first of all, minor corrections. It's a white dwarf. You could call it a star if you wanted to, but to be more extra clear, we'll say it's the remnant of a star, which I'll explain a bit more later. So white dwarf, and the name isn't officially Lucy, it's BPM 37093. But we're going to stick with Lucy for that anyway. So is the white dwarf Lucy made of diamonds? And in order to answer that question, we have to answer a few other questions first. First of all, we need to know, what is a diamond? Second of all, what is a white dwarf? Third, how do you look inside a star? And then, when we know the answer to these three questions, we can answer, is the white dwarf Lucy really made of diamonds? So first part, I'm going to keep these over the side so you can keep track of where we are and know I'm not just going off on a random tangent, which does happen. So, first of all, what is a diamond? Well, diamond is a form of pure carbon. And in this form of pure carbon, the carbon atoms are arranged into a very regular lattice. That's what gives it its extreme dense it's kind of a high packing fraction. You squeeze all those carbon atoms in to a very regular matrix. It's what gives it its material properties. And if you're not familiar with carbon, carbon is the atom with 6 neutrons, 6 protons, and 6 electrons. That won't be relevant for most of the talk, so don't worry about it. But diamond is not the only crystal form of carbon, which is where this gets a bit nuanced, because when we start to talk about if this white dwarf is made of diamond, one thing we need to understand is there are other crystal forms of carbon, such as graphite. Here's the difference. So you can compare these two crystal structures. One is kind of like, this three-dimensional cubic structure is what it's called. And the other is kind of like you have these layers, these sheets that are weakly attached, but within the layer, it has a very strong kind of grid kind of a structure. And so graphite's kind of a softer material because it doesn't have that integrity in that vertical direction. It has really good bonds in each level, but the levels kind of slide between each other because they're only attached by a force called van der Waals force, which is a weaker force. So obviously it's very important, if you're going to answer a question about whether something is diamond or not, the actual makeup of the carbon atoms, what they're doing, how they're laid out, what they look like, that's going to be a critical part of that question. So we need to understand, first of all, that crystal, and all crystal means is, as you see in both of these, the atoms are in a regular pattern. That is as opposed to some amorphous materials. In an amorphous material, it's like you just took a liquid and froze it on the spot, where all of the atoms are kind of randomly distributed, and there's no big scale picture. So, another thing we want to know about crystals that's relevant for this question is crystals represent a lower energy configuration of atoms. If you think about it, as in a liquid and a gas, the particles have a ton of energy and they're bouncing all around the place and they're sliding past each other. And they have so much energy that the attraction and the forces between them aren't really that important. When you cool them down enough, they end up sticking together because they don't have enough energy to escape those bonding forces. So you're going to kind of see an example of that in this. So crystals form when the particles, and this is kind of a general description, crystals form when the particles no longer have enough thermal energy to escape the bonding forces between them. And there's a really cool animation here from a YouTube channel called Aptuit Consulting that I found. I want to credit them for that. Where it zooms in, you see a thermometer here on the left showing that it's a high temperature kind of a liquid. We're going to zoom into the molecular level, and you see these molecules whizzing around. But as the temperature drops on the left, they start sticking together because they don't have enough energy to escape each other, essentially. The bonding forces stick them together. And once you get one little nugget of a crystal, the rest of it grows very rapidly because it forms what's called a nucleation site for them to stick together. And this regular pattern, when you zoom back out, is what creates a solid structure. Having those atoms bonded together in a very regular kind of a crystal, or a regular lattice, is what creates these little nuggets of solid material. Now, if you were to heat that up again to a high enough temperature, the particles would get so much energy, again, they would break free from those bonds and go back into a liquid state. And if you heated that up more, probably a gaseous state. So that's the critical takeaway here that will be relevant when we talk about white dwarfs, is that crystals form when the particles no longer have enough energy to escape bonding forces. And I want to just throw up that, because that was a really nice visualization. And kind of a crystallization bonus content, I was thinking of it as. You can actually cool a liquid down below its crystallization temperature without having it crystallize. It's called supercooling. In this case, maybe I should pause this here for a second. Can I? Oh, I think I just restarted. This is the magic of technology. Anyway, so you can cool it down below its crystallization temperature, and if you never get an initial little nugget of crystal, if it's very static and still, and the particles never get to arrange into that, then it won't actually crystallize. But the moment you jostle the liquid, you get these little nucleation sites, and it freezes instantly because it's already below that temperature. So that's called supercooling. Superheating is the opposite of that, where you can actually heat a liquid up past the boiling temperature, and the moment you shake it, it kind of just explodes. I nearly got in trouble with that when I was 16, doing like a little internship. I had a PhD student screaming at me, "Don't touch it!" So luckily I didn't. Okay, so we now know what diamond is, we know what crystals are. So what is a white dwarf? Well, the simple start to this is white dwarfs are the remains of some dead stars. And if any of you recognize this animation, it's because it's from another channel that I really like and highly recommend. I'm going to butcher the pronunciation, but I think it's crystalize. They do beautiful animations of scientific topics, and I'm stealing a lot of their stuff here, so I felt I had to credit, a big slide to them. So, in a living star, gravity and pressure balance each other out. Gravity is pulling everything inward, and there's pressure from a fusion reaction. Think of like a hydrogen bomb, except 100 million megaton hydrogen bombs going off every second. That's pushing outwards. So to get a sense of the pressure, the strength of that gravity that is constantly pulling inwards on a star, first of all, imagine yourself sitting on a box with a nuclear bomb inside, and it's your job to kind of keep that contained. Then imagine that 100 million times every second, and that's the strength of pressure that you would need to contain that. So what happens then is when the star runs out of fuel, that fusion has to stop. And what I mean by runs out of fuel is that fusion is hydrogen atoms slamming together to form a heavier element, helium. And then helium to carbon. It goes as a chain of reactions. We don't need to worry about too much for this. But essentially, that process of forming a new element releases a lot of energy. So hydrogen forming helium releases a huge amount of energy. And when that hydrogen fuel runs out, you no longer have that fusion to produce that energy to resist gravity's pull. So eventually you get into this unstable situation where the star kind of begins to pulse. It begins to throw off its outer layers. And you can see, again, nice animation of that here. It's called a planetary nebula when these outer layers get thrown out. And you can see really beautiful pictures of these from Hubble. And then what's left behind is a tiny little white dwarf. Now, the caveat here is white dwarfs are left behind for a certain range of stellar sizes. Stars that are, rule of thumb, just think 10 times the mass of our sun and less, roughly. That will form a white dwarf, and beyond that, you're going to get neutron stars, black holes. Those are kind of topics for another day. But white dwarfs are incredibly dense. Oh, by the way, I threw this in here because it's really nice. So, whoops, hold on. This we go. So on the left, that was in the animation, and this is a real image of a planetary nebula called the Cat's Eye Nebula, taken with Hubble. It has a nickname. So I really like that picture, and I realized that must have been the inspiration for that animation because it looks like it matches up pretty well. And the thing about white dwarfs is you see this tiny little speck down here. That is, the kind of scale maybe of the white dwarf compared to the sun, and it contains still about half the mass of that sun. So you're compressing a huge, like the mass of the sun into the size of the Earth, which is an insanely dense kind of thing. I think one kind of idea was if you took a teaspoon of a white dwarf, it would weigh the same as like a big car loaded up with stuff. I think that was roughly the night. I can't remember. Camera can give me a sense if that was right or wrong, but I think it was right. So anyway, in a white dwarf, you have a few different layers. We're not going to get too into the details here, but ignore the bottom part for now and focus up here. We have a hydrogen layer, a helium layer, and a carbon-oxygen core. Now, they don't always have a hydrogen layer. Sometimes the hydrogen gets burned off, and the white dwarf doesn't have any hydrogen on the surface. But the carbon-oxygen core is what carbon-oxygen core and the hydrogen layer are the things we're going to really be concerned with. Again, the carbon-oxygen core it could be a mix. The carbon and oxygen might be separated into two different layers. But it's insanely dense, and this is where we need an important caveat when we start to talk about diamonds. Some of you may or may not have heard about words like degeneracy pressure or degenerate matter. What that really means in simple terms is the electrons, so in a carbon we said 6 protons, 6 neutrons, and 6 electrons. In degenerate matter, it's so energetic and so hot and kind of compressed that the electrons are kind of ripped from the atoms, and what you end up with is a sea of the nucleus of the atoms and the electrons separated. And they're all kind of together in this big hot gas. And it's a gas where quantum physics effects become important. Now, I'm not going to get too into detail on that. It's just a caveat to bear in mind that it's not a regular state of matter. It's a different state of matter, so you couldn't compare it directly to diamond that you would see on Earth. As I said, that's a topic for another day. So, in 1960 to 1961, this is something I really like about this because it was quite a while before they actually got to observe these things. Some theorists, 3 different papers that came out between the 2 years, predicted that the cores of white dwarfs would crystallize once they cooled enough. And part of this is due to the immense pressure squeezing the nuclei closer together. So as I said before, what really determines if something is going to crystallize is, are the forces between the particles important compared to how energetic the particles are? And if it is, then they're going to kind of stick together. They're going to get locked in place. And in this case, because you're squeezing the nuclei together, they start interacting more. So if you have a massive enough white dwarf, the atomic forces or the interparticle forces become more significant. The Coulomb forces or kind of electrostatic interaction. Again, I'm just throwing some of those things out there. If you don't know what those mean, it doesn't really matter. However, at this point in 1960, 1961, it wasn't clear how you would test this. It was a nice idea, it was a really good theory, but how could you look at a white dwarf and say, oh yeah, there's crystal in that? So, to do that, you would need to look inside a white dwarf. See how I'm doing on time? I paused the timer. Okay. Well, camera's there somewhere. So how can we look inside a star? Well, to start off with this, I think it's easier to ask, how can we look inside the Earth? I'm going to correct that. And the answer to that, in simple terms, is seismology. Seismology is the study of earthquakes. By looking at an earthquake, earthquakes send waves traveling through the core and through the mantle of the Earth. And how those waves, kind of the direction and the speed of those waves, depends on the densities and the depths of the different layers of the Earth. So if you have a hard nugget in the center, some of the waves are going to rebound off it. If you have kind of soft material, it might carry the waves better. So as you can see up in this diagram here, the waves are originating at the top, and then the core is blocking some of the waves. It's allowing some of the other waves to go through. So the kind of resultant surface waves depend on what happened inside. So if you start off a wave up here, what kind of happens around the rest of the surface of the Earth depends on what the Earth is made up of. If the Earth is made of jelly, it's going to be much worse. If the Earth has a very hard, solid core, it's going to deflect some of the waves. So there's a relationship there between the tremors you experience at different points on the surface and what the Earth is made up of. So just to kind of drive that point home a bit more, if earthquake originates here, and you have people standing here, and telling you what waves, what tremors they're experiencing, you could get all of those measurements and reconstruct an image of what the inside of the Earth must look like in order for them to have experienced, for example, down here in these gray areas, there were no tremors because the waves never reached there. And over here as well. There's kind of weak, different types of tremors here. So you could get all that information, piece it together into a computer model and say, okay, here's what the inside of the Earth must look like. The same thing is true for stars. And one of the questions you might immediately ask here is, well, where does the earthquake come from in a star? Well, stars, they don't have earthquakes, but they pulsate and they vibrate for different reasons. Typically, it's associated with some unstable process where you have kind of a runaway heating that increases the pressure so the star expands, but then it expands too much, it cools down, and it starts to heat up again. And then now it's hot, so it expands again, and you have some kind of this cycle of heating and cooling. That's one example of how you might get pulsations in stars. But there's a lot of other complicated, like convection mechanisms. Imagine like the atmosphere, like turbulence, like really, on Earth, if you imagine just kind of like when you get like very hot and cold weather, it creates big wind patterns. You get convection, you get a large-scale bulk movement of the gas. You have that, but more extreme in stars, where the hot and cold regions cause kind of convection flows. And sometimes what you can get is, for example, like one big upwelling of material, and it gets pulled back down by gravity, and then that causes a wave to travel. That would be called a G-mode wave, similar to water waves on the Earth. They travel they're pulled back down by gravity, and they're pushed up by something that triggers the wave. So in this one here, what you'll notice, and this is kind of important too, it's very, very small kind of movements. This isn't a huge, and even this is exaggerated. So if you're looking at a white dwarf, if you're looking at a star, the kind of perturbations and the vibrations that you see are actually very, very slight. So you have to have really accurate assessment of what you're seeing. And the tiny changes in kind of the shape of the star, they change the size that you're seeing. And so if you're seeing more or less of that surface, it gets brighter or dimmer. Right? So if these kind of pulsations correspond to kind of brightness pulsations. So when you're looking at the star, it'll get brighter, it'll get fainter, and you can track that. So for example, if you wanted to study a star, a white dwarf, doesn't really matter what it is, and just in simple terms, you look at it on Monday and you go, okay, it's that bright. Then you look at it on Tuesday, it's a bit brighter. You look at it on Wednesday, it's gone back down, it's gone down further on Friday, up again on Saturday. And you might look at this and go, hold on a minute, that looks like a nice little sinusoidal kind of wave. Like that's a simple, single mode of vibration. And this is the kind of vibration you see in a lot of very simple systems on Earth. And so you might want to get more data and do peer-reviewed research before you claim that there actually is a vibration in that. But the important thing is, this is an example of a single mode, one kind of up and down oscillation that's not very complicated. In truth, you typically have more than one vibration in a star. So for example, if you have 3 different types of vibrations all added together, call them mode 1, mode 2, and mode 3, the kind of red, pink, and green. If you add those all together, you get this bottom one, which looks a lot more complicated. So if you were to observe this in a star, it would not be immediately obvious what you're looking at, right? It would take some careful observation, some careful kind of clever methods to figure out that this is actually a combination of these 3 individual vibrations. So the pulsations in a star are often a complex mix of many simple modes added together. And this is a really important concept for how we look inside a white dwarf and understand if there's crystal there. Because white dwarfs, some of them pulsate, and we need to be able to identify maybe 3 or 4 modes. And kind of that tells us a lot about the star. So here's a little bonus content as well. Here you have 2 simple, these would be similar to G waves, right? They're waves that are pulled back down by gravity after they get excited by the 2 bouncing green balls. And you see when they kind of coincide, you get a more complicated pattern emerging. So if you were just taking a picture of that, you would need to have some understanding to be able to reconstruct that that's actually 2 simple waves interacting. So that's similar to how we approach stars. By observing them for long enough and by applying the right methods, again, I'm going to throw out a term that whether or not you know it, it doesn't really matter that much, but we use a process called a Fourier transform that takes a sequence of squiggles and essentially turns it into individual simple vibrations or simple modes and tells us what the frequencies are. Like back in this slide, I didn't have an x-axis here telling us what the time is, but you could imagine that this one it oscillates once every like 10 seconds. This is once every 5 seconds, and this is once every, it looks like about 5 as well. So those would be the periods, or you could change that into a frequency. How fast is it oscillating? So understanding the different periods, the different kind of speeds of oscillation of the different modes in a star, that gives us an understanding of what the star is made up of. So the unfortunate thing is when the initial theories about crystallization were suggested, nobody had ever seen a pulsating white dwarf. And in fact, it was 30 years later, in the 1990s, before a viable candidate and a viable method to observe a pulsating white dwarf and understand these sides of it emerged. And that candidate was a white dwarf casually called BPM 37093, because at that time it wasn't nicknamed Lucy. So, now we've learned about diamonds, we've learned about what a white dwarf is, and we've learned about how extracting the different pulsations of a star can give you information about what's inside the star. So we're ready to answer this question of, is the white dwarf Lucy really made of diamond? So in order to do that, I'm going to take a bit of a gamble here. I took a figure from the paper that actually suggested how you would test this. And as you can see, it's a really low-resolution, awful figure that I don't expect anybody here to be able to make sense of. So I've kind of modified it myself. So along the bottom, what we're seeing is the amount of crystal in the core. So things over on the left have no crystal, and things over on the right, all crystal. On this axis, the separation between the different modes. So if the first mode was once every 1 second, the second mode was once every 10 seconds, maybe a separation of 9 seconds between those two modes, right? So how far apart are the different vibrations in terms of how fast they move? And then this line in the middle, I'm just making that clearer. So what you're seeing here is essentially a trend that down in the bottom, where there's very little crystal, there's very little separation between the frequencies of the different modes. So they're all oscillating at more or less the same frequency, relatively speaking. And up in the top right, they're more spread out, they're more separated. The frequencies are more different. So you have a much slower one and a faster one. So what you're seeing from this is, as the crystal grows in the core, the different vibration modes spread out in frequency. They get kind of relatively more different. This is all kind of normalized, but I don't want to get into too much on that. So basically the gist is, if you were to look at, I have an example here actually. So let's say you were to look at vibrational modes in a star, and you observe 3. One pulses every 102 seconds, another one pulses every 189 seconds, another one pulses every 330 seconds. You could use that information now to pump it into a computer model that would give you information about what the inside of that star looks like. And it's kind of it's a complex, they usually do this on numerical kind of simulation, so they need a supercomputer to run a bunch of, there is kind of a very equation-heavy way of doing this, but the way they got this line was by running models on a computer. So you can do this to give you an idea. If you observe something like this, you can get a grip on what's inside the star. So here's what we need in order to test if there's a crystal core in a white dwarf. First, the white dwarf has to be pulsating. Second, we have to be able to measure a few different modes and understand what the separations are between the modes. And third, the white dwarf should be massive. And the reason for this is that white dwarfs cool very, very slowly. They cool over billions of years. So the chances of a white dwarf really cooling down enough to form a crystal are normally very low. However, if you have a massive white dwarf, as I talked about earlier, that pressure squeezes the particles closer together. So those forces between the particles become stronger in a massive white dwarf. So the bigger the white dwarf, the stronger those interparticle forces are. So in bigger white dwarfs, you're more likely to get a crystal. So here's why Lucy is special. It's a variable white dwarf, so it's pulsating. It has 4 independent observable modes that they were able to measure. And it has an unusually high mass of 1.1 solar masses, meaning it is 10% larger than the sun in terms of its mass. So that is huge. White dwarfs are normally not nearly that big. So it's an extreme outlier in that sense. So, whoops, spoiler. So in 2004, pretend you didn't see this already, these 3 astronomers, Metcalfe, Montgomery, and Canaan, I don't know if I'm saying that correctly, they have tested crystallization theory in this star. They measured 4 different modes, and they tested the separation. They ran their computer models, and their conclusion was that Lucy's core is 90% crystallized. So almost the entire thing, almost a full solar mass of crystallized carbon, or oxygen. They ran 2 different models, one assuming maybe it's all made of carbon, maybe it's all made of oxygen. They think it's made of oxygen, but carbon is closer to diamond, so that was more fun. But they do think it's more made of oxygen. And then, much more recently, I was surprised to find it was interesting. Last year, 4 more crystal white dwarfs were discovered, and they had crystallized fractions of 50 to 70%. So Lucy, while it was the first one and the kind of best candidate with a lot of crystallization, is not a standalone paper, and there have been other confirmations of this theory. So is Lucy really made of diamonds? Well, no. But it is a solar mass of crystallized carbon ruled by quantum physics, and that's way cooler. Thank you. So yeah, I'm happy to take questions. And also, I threw up my email here because, as you know, this whole talk, I wouldn't have ever learned about this if it wasn't for an email from a middle school student. So I highly encourage you to send me if you have questions. And even, I don't care if you think it's a silly question, just email me anyway. I'll do my best to respond to them. I do enjoy this kind of stuff. It's procrastination at its finest. So, and now I'm happy to take questions as well. Yes?
So how would degenerate matter crystallize?
So that's the interesting thing, is that in degenerate matter, as I said before, and I had to spend quite a while understanding this myself because it gets complicated. If you think about it like it's what's called a Fermi gas. So it's a gas of these kind of particles, nuclei and electrons. And although it is that gas, if you squeeze them together again, the nuclei can kind of get fixed into place. So the electrons continue to stream through the whole thing, and they continue to be degenerate. But the protons end up kind of being kind of fixed together in that crystal structure. That's my best understanding of it. A compact matter expert could probably give you a better one. Yes?
So in white dwarfs, where they're really super dense, and we now have this kind of like sea of electrons surrounding the compressed nuclei.
Mm-hmm.
We were talking about their quantum state. Are they? I mean, is this a giant mass that's all in superposition? Like they're both Allison Bob at the same time?
So, in a way, yes. So the idea of degenerate matter is... So, so what makes it diamond is the kind of crystallization of like the positions of the nuclei, right? The electrons remain degenerate in the sense that what degenerate means is essentially when they're all in this one quantum system, they can't. No two electrons can occupy the exact same quantum state. So in that sense, the whole system is one quantum system where the electrons have to obey this rule that they have to fill higher and higher energy levels, and there's kind of no room. And that's part of how you explain why it takes so much energy to squash it down more. That's where the degeneracy pressure that pushes outwards comes from. In terms of it being a superposition state, I don't think it applies in that way, in the sense that it is a crystal structure. And the superposition... I'm not sure if the superposition applies to whether or not it's a crystal. Yes?
So is there a crust at all to the white dwarf?
Sorry. I thought you were. So that's an interesting question, because the material that makes up the core of the white dwarf, although in most white dwarfs, let's say where it's not crystallized, the material that makes up the white dwarf, it behaves in a lot of similar ways macroscopically as a solid, even though it is a liquid. That's just because it's so incredibly dense. The crust, not so much. There's an atmosphere. There's kind of a hydrogen, the less dense hydrogen and helium atmosphere. So whereas the Earth has this kind of crust on it, in a white dwarf you have these kind of gaseous atmospheres, or probably degenerate hydrogen and helium atmospheres. Yes?
I have a question. How far away is Lucy?
Ooh.
And with more modern telescopes, are you able, with like full sky scans, are you able to monitor at the level that you need to do this kind of analysis in a more broad way? Is that why your candidates are being found? Or do you still need 0.1 narrow field telescope at a candidate in order to get this data?
So to answer the first part, I don't know what the distance is, but we could totally look it up afterwards. I'm happy to do that. With regards to why they kind of found four more, yeah, I think you're absolutely right. Is that over the last decade or so or more, there's been like just an incredible increase in the survey capabilities of, especially here at Caltech. One of the biggest things is the Palomar Transient Factory and now the Zwicky Transient Factory. These powerhouses of finding like pulsing and kind of appearing and disappearing objects in the sky, and also bigger and better telescopes, more sensitive instruments. It is, I think, just a result of better capabilities.
Is Lucy still the biggest one that we know?
I think so. I think, yeah. Yes?
In your model, you spoke about the white dwarfs shrinking from the size of the Earth, of the sun to the Earth,
Mm-hmm.
and having a mass of 10 solar masses, and yet Lucy's at 1.1 solar mass.
Mm-hmm.
Is this just an outlier to that model?
So the maximum of 10 solar masses applies to the star that originally forms the white dwarf.
Right.
It's a very good question, because what happens is a lot of mass gets lost before the white dwarf gets formed. So you could have a star that's like the mass of the sun, but then by the time it forms the white dwarf, it's already ejected half of its mass. So in the planetary nebula, a lot of the stellar mass gets thrown out into space. So typically, you lose a huge fraction of the mass in the formation process. So the upper limit on white dwarf mass is set by kind of quantum physics rules, or set by some gritty physics that I honestly don't fully understand myself, but based on classes, I know that much. But it's about 1.38 solar masses, and it's determined by kind of how much that electron degeneracy pressure can resist gravity. After that, it collapses even farther to a neutron star. And yes?
What are the future type of concepts or ways that you would further your research? Or do you think that this is possibly the best way to figure out what you're looking for?
So this isn't my research. But if I was to ask, what direction I think this would go in future, I think one of the biggest things is probably what we were talking about a moment ago, about getting many more samples of this so you can really put the theory to the test and understand, because they do this all through computer models, right? So if you only have 2 or 3 models, your results are kind of, less confident. The more samples you have and the more you can test this theory on different independent observations, the more confident you can be in your results. So I think the kind of survey capabilities and getting many more of these objects is probably the next step in that field. Yes, last question, sorry.
I just read an article this week that geologists on Earth using seismology are guessing that there's about a quadrillion tons of diamond in the Earth, in the crust, about 150 to 200 miles down, which is way out of our drilling.
Wow.
My question is, do you think that there's kind of conditions on Earth to create that mass of diamond?
So to create that mass of diamond, well, because the mass of the Earth is so much smaller than the mass of the Sun, because what we're talking about here is like diamond as much as the mass of the Sun. So we don't have enough material on Earth to form that much. And whether or not you could form this type of material, like this degenerate diamond on Earth, you don't have the pressure conditions to do that. As for I'm not sure of what the upper limit on how much diamond you can form in Earth is, so I'm afraid I just don't know that. Cool, thanks.
Okay.
Cool. Oh, and I'm going to be happy to take any more questions if you didn't get a chance to ask here. So, that's back to
Please thank our speaker, Donal. All right. Thanks for sticking around, everybody. So this is our expert Q&A panel. We're happy to answer questions as best as our ability allows. If there are planet questions, I'll give them to our recently PhD doctor in the back row from the Planetary Science Department, who's here. But our Q&A panel consists of Dylan. Dylan is a graduate student in the department. He's happy to answer questions about supernovae, gamma ray bursts, star formation, and radio astronomy. Sarah Blunt is an undergrad starting graduate school at Harvard in 1.5 months. Sarah's happy to talk about exoplanets, stars, and white dwarfs. Nikita is a graduate student in the department, and she will happily talk about black holes, X-rays, and active galactic nuclei. And hey, Gotham. I'm Cameron. I'm a postdoc in the department, and I will talk about anything you want. But the things that I feel most comfortable talking about are simulations of various different types, but galaxies and cosmology. So we open it to you guys. You guys can answer or ask us questions about whatever, and we'll try and address it as best we can. Any questions? No questions. Okay, lots of questions. The gentleman in the back was first.
Just continuing with from the talk.
Yeah.
So I'm puzzled as to how it's not a real crystal in the sense that we usually think of it, because crystals have molecular bonds, but this is a quantum solid. And so is it just
Like, what's the difference? And is this... I mean, it's a crystal in that...
is it just close packed like a bunch of oranges? You just pack them as close as
I wouldn't say that. Like, yes, they are closed packed, but rather than molecular bonds, chemical bonds holding these things into a lattice, it's the degeneracy, it's basically the fermion bonds that are between these that are keeping them in place. And I don't think it's the same structure, like a tetrahedral structure, but it is a lattice of that's regular in terms. Yes, it should be regular. So it really is a crystalline, in my understanding. I don't know. Okay. Sorry, I'm not going to take all the questions. I just thought I could address that one. The gentleman in the back.
So the center of the white dwarf, you've got this different crystalline structures. Is all motion stopped? And if so, does that mean that time no longer exists?
Oh, whoa. Well, you really took a step there. So starting with what you finished, time does exist, but in terms of with degeneracy pressure, there's motion, in particular with the electrons, but with the nuclei, it should be more stable because they're more massive, and they're basically held in place by the electrons at some level. So I don't know.
Yeah, so I guess the only way that you could ever get zero motion is if you cooled it to absolute zero, right? And because it has a temperature, it's probably like, a few thousand degrees or something. It's gonna, the atoms themselves are still gonna vibrate, but overall they're gonna stay in their regular pattern because even though they want to vibrate away, there's just so much stuff that's pushing them in. The rest of the star is, right? They're forced to stay in that regular configuration because that's the lowest energy state.
I guess one more small thing I could add is that the white dwarf is continuing to cool over time, so it's changing, and so as long as there's some sort of change happening, you could sort of infer that time keeps going.
He was saying that white dwarf limit is 10 solar masses. Anything smaller would create a white dwarf. But then he also said that white dwarfs maximum size would be like 1.38. He said something like half the mass is lost. So is it on the bigger ones, they lose more than half? Because how does it go from 10 solar masses to 1.3 solar masses?
So I think he was just trying to give an order of magnitude sense. He wasn't necessarily saying that it has 10 and then it loses half and then it's 1, because that doesn't work. But yeah, I think depending on the mass of the white dwarf and the composition in particular, they can lose, I don't know, I think like more than 50% of their mass in some cases and a little bit less in other cases.
Yeah, so I guess the white dwarf itself is actually just the core of the star. All of the atmosphere has been lost to that planetary nebula that Donal talked about. Right? So that gets rid of a lot of the mass. As for how do you get rid of, how do you go from 10? Actually, I think the line that people think stars explode in supernovae compared to blow off their outsides in planetary nebulae, I think it's 8 solar masses. But there's some uncertainty about that. As for how you get rid of that mass, a lot of times it's due to sort of opacity in the atmosphere, where light that's generated from inside the star will actually push the gas outwards. And because later in a star's life, stars tend to puff out a whole ton, you don't actually need that much momentum being transferred or that much energy being transferred to actually get that gas to escape out into space and never come back, right? And so that's generally how like mass loss works in stars. Mm-hmm. Oh, yeah.
So then to answer the last part of your question about why is it 1.4 solar masses or so, is because as the star is collapsing and you have this state of degeneracy pressure within the core, you basically, there's some physics that you do that's called there's a scientist called Chandrasekhar who derived an upper mass limit that these white dwarfs cannot exceed. Because if they did exceed it, then essentially gravitational instabilities would take over and it would just collapse in on itself. So that's why there's like this magic number that Chandrasekhar derived that's 1.4 solar masses that white dwarfs can't exceed. And you go into a bit more complicated things like it's the electrons are going from being non-relativistically degenerate to ultra-relativistically degenerate, which is probably too complicated for this level.
But one can just understand it in that as something becomes more massive, as a white dwarf becomes more massive, it needs more pressure to hold itself up against the gravitational force that's pulling it in. And above a certain mass, the quantum speed of those electrons becomes faster than the speed of light. And so you can't exceed that, so it just collapses. So that's kind of the intuitive understanding of it.
So when it turns into, it gets too big, or the mass gets too large, it turns into a neutron star.
Well, more likely what happens is as it gets more, I mean, this is what, did you guys say type 1a supernovae? Yeah. So, yeah, as it gets more massive, and sometimes this happens when you have a binary system where one of them is a white dwarf and one of them is just like a normal star, and it slowly rips off material from the normal star to like feed the white dwarf. So it gets more massive and more massive and more massive, and once it becomes greater than this Chandrasekhar mass, this 1.4 solar masses, it just turns into a big bomb. And that bomb is called a type 1a supernova, and we see those in space. So you never see a white dwarf that exceeds this mass, because if it ever goes above that, it blows up. It's a big explosion.
So neutron stars happen when stars that are initially more than 10 solar masses reach the end of their lives. So there are different types of degenerate kind of end states for stars. So the stars that are 10 solar masses and below turn into white dwarfs, and then the next category up turn into neutron stars, and then the biggest turn into black holes. Maybe we could just say a sentence each about what we do, just to kind of let you all know.
And then if you have any sort of questions branching out from something that we said, then just feel free to ask away.
Oh, okay. I can talk about my science. So I run computer simulations, hence the simulation thing on my list, of galaxies and cosmology. So I do big computer simulations that I represent a very large volume of space on the order of 300 million light years across, and then populate it with a distribution of material that's on par with how the universe looked really early in its evolution, just after the Big Bang, and then program in gravity and hydrodynamics, how fluids interact, and run it forward and see if it forms the kind of galaxies that we see when we look up with our telescopes today, to try and understand how galaxies form and how they evolve over the age of the universe.
So I study black holes, specifically supermassive black holes. And the kind of supermassive black holes that I study are these black holes that are accreting a lot of matter. And these black holes are called active galactic nuclei. So they're these galaxies that are really, really luminous because at their center they've got this supermassive accreting black hole. And I study these black holes in the X-rays. And I use a really cool telescope called NuSTAR to do this. It's the first telescope out in space that can actually focus really high energy X-rays. So X-rays are different from other types of electromagnetic radiation, and that is actually really, really hard to focus them. But NuSTAR is the first telescope that can actually focus these really high energy X-rays, and this can give us a lot of information about, by studying these X-rays that are coming from these black holes, about how is the matter falling in, what's the geometry of the black hole, what's its shape, and cool things like that.
Some of the people I recognize have been to some of these before, have maybe heard me say this before, but I'm a planet hunter, so I look for planets outside of our solar system primarily, and that can get really complicated because planets exist around stars, and stars are really weird, complicated objects that we wish were simpler, so we could just find planets around them really easily. And I also have recently been working on a project trying to figure out what binary white dwarfs look like in the galaxy. So two white dwarfs that are orbiting around each other really closely, the way that Earth orbits around the sun.
So I primarily work with a telescope called the Very Large Array, which is 27 radio dishes that live out in the desert of New Mexico, and you combine their signals to form essentially one very large telescope that has really good resolution. And so I study two different kinds of objects using the Very Large Array. Previously, what I did was I pointed this telescope at star-forming regions in nearby galaxies to be able to understand how we can more accurately measure just how fast stars are being born in these regions. And as of late, what I've been doing is I've been working on this gigantic survey called the VLA Sky Survey, where we're imaging the entire sky 3 times over the next 6 years, and basically just looking for sources that appear and disappear. And these will be candidates for afterglows of supernovae, of gamma ray bursts, of these events called tidal disruption events, where a star gets ripped apart by a supermassive black hole. All sorts of cool things can happen when you introduce that 4th dimension of time into astronomy. Mm-hmm. Yeah. Mm-hmm.
When you use the VLA, can you image more than one part of the sky at a time?
Yeah. So the question was, when you use the VLA, can you image more than one part of the sky at a time? So I guess there's a field of view to the VLA, right? There's what's called a primary beam. So there'll be, if you point all 27 antennas at one location, there will be some part of the sky where you're super sensitive to any radiation that's coming in. And elsewhere in the sky, you won't really have any sensitivity at all. What you can do, though, is you can break the VLA up into subarrays. So you don't have to point all 27 antennas in one direction. You can point, 13 of them in one direction and 14 of them in the other direction, right? And that way you can image 2 parts of the sky at once if you really wanted to. Oh, yes. Mike, if you want to introduce what you do as well. Mm-hmm.
Wait, what?
Someone asked what you do.
Oh, okay. I'm a planetary scientist from across the street, and I really like thinking about astrobiology, the search for life elsewhere, and understanding what makes planets habitable and fit for emergencies of life. And I do this mainly by studying planetary atmospheres and running simulations of the chemistry inside atmospheres of other places in the solar system, and soon to be doing that about exoplanets, planets around other stars, at a postdoc that I will move to in 3 months. So.
Yeah.
I just wanted to have a question about white dwarfs. If I understand, they no longer have nuclear fusions going on, is that correct? But obviously we can detect them, so there's other types of energy, visible light still that's coming from them, but they're fainter. So then just the process of what's still going on to make energy, and then being so small, what's the furthest we've detected them? Are they relatively nearby in our galaxy, or can we see them much further out?
That's a great question. So your question, I think, had 2 main parts. The first part was, if we're seeing white dwarfs, there has to be some sort of energy coming off of them. So where does that energy come from? And then your second question was, white dwarfs are fainter than stars. So it must be harder to see them, so there must be some distance beyond which we can't see them anymore, which is true. So the first part of your question, just because something isn't actively producing energy doesn't mean that it doesn't have some energy left over. So when a white dwarf forms, it is no longer undergoing hydrogen fusion or other type of fusion in the core. So it's not actively radiating away energy that it's sort of creating, quote unquote, in its core, but it still has a bunch of energy that it's radiating as heat. And so you can think of it like the energy is stored in this sort of in gravitational energy, in potential energy. And so as the white dwarf cools over its life, that gravitational energy will get converted into this light that's being radiated away, and it'll sort of cool and contract over time. So there are other sources where that energy comes from, but yeah, that's one way of thinking about it. And then the second part of your question is that you were completely correct in that we can't see white dwarfs out to a certain distance. This is true of stars too, actually. There's a certain distance beyond which we can't see like individual stars. We can't even really resolve individual stars in other galaxies very well. And certain types of stars or other objects we can't see out past a certain distance. But yeah, so I think the farthest we've ever seen a white dwarf is a few parsecs out. So a parsec is like 3 light years-ish. So on the order of 100 light years, I would think, is the farthest away white dwarf. Yeah, so people are actually really excited about the potential of gravitational waves to detect white dwarfs, because the gravitational wave signal of orbiting white dwarfs, so binary white dwarfs that are really close together, is really, really strong, whereas their light signal is really faint. So it would be really hard to see a white dwarf with your eyes or with a big telescope on the other side of the galaxy. But if they're really close together and they're orbiting really fast, we could detect them in gravitational waves. So it's like an earthquake in space-time. It would be awesome.
So there is an indirect way to detect white dwarfs out to cosmological distances, almost to the edge of the universe. And this is when they explode in Type 1a supernovae, as Cameron was saying earlier. And this is actually super important for cosmology and for our understanding of how the universe is expanded over time, because we think that Type 1a supernovae are what are called standard candles. Actually, it's a bit of a lie. They're standardizable candles. So basically what it means is that we can take observations of these explosions and we can figure out exactly how bright the explosion was. And not just like exactly how bright it looks to us, but exactly how bright it actually was if you were standing right next to it, right? And based on comparing exactly how bright it actually was to how bright it looked to us, we can tell how far away it is. And there are other measurements, or there are other ways of measuring how far away things are. And by comparing those two distances that you measure, you can get an understanding of how the universe has expanded over time. Yeah.
Yeah, wouldn't the absolute luminosity of a Type 1a supernova really depend on the chemical composition? For instance, Donal was talking about white dwarfs composed of oxygen and carbon. If you have as we keep piling more and more matter onto one of these white dwarfs and that goes off, it would seem that you've got a whole range of possible elemental compositions of these things. So when you talk about absolute luminosity, how accurate would that be?
Yeah.
It seems like that would really, the idea of the accelerating universe and all that would really depend on whether you've got a real tight control over those luminosities.
So Type 1a supernovae were actually classified first observationally. So people looked at these types of supernovae and they said, hey, this supernova looks exactly the same as this one. It looks exactly the same as this one. It has the same exact structure as this one, except it's fainter a little bit. It's farther away. So people first figured out that there was this class of explosion that had these similar characteristics. And they used that to kind of backtrack the theory that this could happen if a white dwarf was accreting from some other thing and exploded. And you're totally right that it depends on the type of explosion you would get would depend on the type of the chemical composition of the white dwarf. And we know that there are different chemical compositions of white dwarfs, but we don't really understand exactly how Type 1a supernovae work. So I don't actually know, but I would assume that it's just one particular type. Like that, yeah, do you know more about this?
A little bit, yeah. So I was saying earlier that Type 1a supernovae aren't exactly standard candles, but they're standardizable candles. So there's a relation, I think it's called the Phillips relation, where basically the longer the light lasts from a Type 1a supernova, the more intrinsically luminous it is. This is a pretty small effect. All Type 1a supernovae are all pretty much the same. But if you really want to get the second decimal point, then you have to look at how long it lasts. And that, I believe, does depend a little bit on the chemical composition. To throw a further wrinkle into this, it's now thought that most Type 1a supernovae aren't actually due to a white dwarf piling on matter from a companion star and getting over the Chandrasekhar mass. It's thought that most Type 1a supernovae are probably the collisions of two white dwarfs. And so, the physics of that is a lot messier, and there's still a lot to learn about this stuff. But empirically, you can actually show that it is the case that the intrinsic luminosity does depend on, to first order, just on that one parameter, which is how long the supernova lasts. Right? And you can get the intrinsic luminosity because you find Type 1a supernovae in nearby galaxies where there are other methods of determining exactly how far away that is. Mm-hmm.
Yeah, so we don't understand Type 1a supernovae super well enough, but yeah.
Yeah, I mean, we do have like some theories out there that we don't know if it's really, it's untrue to say that it's because you've got accretion from a companion that, piles up matter and it exceeds the Chandrasekhar mass limit. There is no requirement that the white dwarf has to exceed the Chandrasekhar mass limit. Really, all you need to get that explosion out is to ignite carbon burning. So there are all these sorts of processes that take part first on the surface of the white dwarf, and these are like surface detonations that can happen, and then eventually it cascades down and you get a detonation in the core where you got carbon burning ignited in the core, and then that sets off the huge explosion that we see as the Type 1a supernovae. So in that sense, about how composition would drive the luminosity, well, at the end of the day, the process is something along the lines of carbon burning is happening in all of these different types of white dwarfs. So I'd say there might be some small differences in the spectra depending on, individual composition, but I think they're all similar enough that they are fairly standardizable to some extent.
Okay, I know there's no such thing as a dumb question, so here goes. Do you have an idea directly or otherwise how many black holes are in the universe, and could that result in a big crash in the Big Bang?
Okay, so the question was, do we have some kind of estimate of how many black holes are there in the whole universe, and are there enough of these black holes that, matter could be sucked in to form some kind of big crunch? So we have black holes, and they vary in their sizes and how much mass they contain. So when very massive stars die, they can collapse to form a black hole, and we call these stellar mass black holes. And these are ubiquitous in any galaxy that you find. So you would have many millions of black holes that are stellar mass sized in a given galaxy. And we believe that at the centers of most galaxies is a supermassive black hole. So that's what I study. I study supermassive black holes that reside at the very centers of these galaxies. And what's interesting about them is that we don't really know how supermassive black holes form. If we look at galaxies that are really, really far away, we see that they still host these really, really massive black holes at their center. So even when the universe was really young, somehow you've got these humongous black holes that have already formed at the center. And it's still an open debate about how can you form these really massive black holes so early in the universe, and how are they growing so exponentially over time. So the question about, are these black holes, big enough, and are there enough of them to suck matter in? So while galaxies individually are bound by gravity and so on, a black hole in and of itself can only, suck matter in within a certain radius, and we call this the event horizon. So, no matter what kind of object that you have, and no matter whether it's light itself, if it's outside of this event horizon, then it's not going to fall into the black hole. So, and then to go on to talk about the scale of the universe as a whole, even galaxies, while they're bound together by gravity, the expansion of the universe, which is driven by this mysterious dark energy that we don't know about, is still a dominant factor, which is why all these galaxies are still receding from us, and we're all moving away. So if anything, our universe is going to end up in a, what's the opposite of a big crunch? I know, but what was the opposite? Big group, I guess, where, galaxies are just so far apart that, the universe just becomes cold and dead. So the possibility of these black holes sucking in matter to form a big crunch is not likely.
I thought that was a really good question, by the way. Not a stupid question at all.
Just really quickly, we think that there are, I think, a couple 100 billion galaxies in the universe, and we think that at the center of every single galaxy, there's a supermassive black hole. So if you just want a number, at least a couple 100 billion. But, for every supermassive black hole, there are probably a lot more smaller ones. And so I did the very, very rough numbers in my head, and I think it's 100 trillion or something like that. Yeah.
How much more massive is the super black hole than the normal black hole that's created from a collapsing star? And how many times would a black hole need to merge, essentially? Two black holes need to merge in order to become a super black hole?
Okay, so the question was, what are the mass scales for a normal black hole versus a supermassive black hole? And going back to what I was talking about earlier, how can you even get to supermassive black hole scales? Can you get it from just merging together black holes? So for your first question, regular black holes that are formed from the collapse of a massive star are of the order of a few solar masses. So if you take the mass of the sun, that's typical mass of a regular black hole that you find within the galaxy. Supermassive black holes tend to range from millions to up to 1 billion solar masses. And you can't really get them from just merging two black holes together, because you can't take one solar mass and one solar mass black hole and end up with 1 billion, obviously. So some theories that are out there about how we can form these supermassive black holes is that it could just be that, especially very early on in the universe, you just have direct gravitational collapse of matter. And that direct collapse of matter just keeps on growing over time as the initial baby black hole that was formed just keeps on accreting matter onto it, and eventually grows to supermassive black hole scales. Other theories are that there are these certain types of stars called population 3 stars, which are these really, really massive stars. So it's possible that supermassive black holes could be formed from when these types of population 3 stars die, that they can form the seeds for the formation of these supermassive black holes. And then there are also theories that, merging of galaxies together, galaxies can collide, and then if each galaxy has a supermassive black hole in its center, you merge those two galaxies, and then you can get an even bigger supermassive black hole that way. So those are some of the theories I know of. Do you guys want to add to that?
That's a really stupid question.
No stupid question.
Black hole is simple in the sense that it has mass, angular momentum, possibly charge. Do they also conserve baryon number or lepton number? And if they do, how do we know? Or does everything just get wiped out? I think this is kind of related to the information.
So the thing about black holes is, like you were saying, there are very few parameters that we can, or properties that we can characterize about them. One is the mass of the black hole. The other is the overall charge state, whether it's neutral or positive or negative. And then the other property that we can measure of the black hole is how it's spinning and how fast it's spinning. But other than that, once matter falls into the black hole, we have no idea what's going on inside it, what kind of reactions could possibly take place in it. And there are all these kinds of, theories about, quantum gravity and weird effects that might be going on inside. But yeah, once a particle passes the event horizon, it's unknown what kind of state matter is in. So it's hard to say whether we know anything about conservation of charge or baryon number or anything like that.
Yeah, shifting gears to simulation. So how are you simulating dark matter?
Okay. So the question was, for simulations, how do we simulate the presence of dark matter and dark energy in the simulations? So for the types of simulations that I do, as I said, you have a very large volume of space on the order of like a few hundred million light years across, and we populate the simulation with different types of matter, one of which is baryons, which is to say protons and electrons and neutrons, the kind of stuff that we're made of and all the things that we interact with on a daily basis are made of. And then we also populate it with dark matter. Now, the main way in which dark matter is represented in our simulations is as individual particles. And when I say particles, I don't mean subatomic particles or anything like that. The simulations, because they're so large, we don't have infinitely high resolution. We're already running on supercomputers, and we wouldn't be able to do that. So usually the spatial and mass resolution of our simulation, a particle might weigh something like 1,000 solar masses. So quite a bit. We wouldn't be able to resolve a star or the sun or the solar system in our thing because it's this huge volume. So dark matter particles are 1,000, or sometimes if it's a low resolution simulation, 1,000,000 or 10 million solar mass particles. And whereas the gas and the baryons are usually either represented as particles or as a grid structure, like a normal lattice, a normal array, where you allow gas, because the bulk of the matter in the universe that's in baryons is gas. There's not a lot of solid state matter. There's not a lot of planets. Most of it is just big gaseous structures. And so following the evolution of how that gas interacts is very important. So that's why we include hydrodynamics and the behavior of gases as they interact in the simulation. But in terms of dark matter, it's primarily as particles that have mass, but they don't interact with the gas in other ways, like electromagnetic forces or anything like that. They just influence things by the presence of their mass and gravitational effects. Does that answer your question?
Yes.
Okay, cool.
Related to that, I think I read recently that one thing that doesn't match simulations is that you expect, because of the dark matter halo, that what do you call it? Small galaxies around big galaxies should be distributed, spherically. That when you go measure, they're all kind of in a big plane. But is that the kind of simulation that you do that would analyze that? Or is that a different kind of simulation?
Yeah, it's related to what I do. So the question was, in simulations, one of the problems that we're currently studying is why galaxies and the distribution of galaxies isn't necessarily symmetric, and you don't have spherical symmetry in terms of how dwarf galaxies, smaller galaxies, orbit around larger galaxies like our own Milky Way. And this is definitely something that there's a lot of research going into, including people here in this very department who are working on this, and some of my colleagues. Yes, in our local group of galaxies, which consists primarily of the Milky Way, our galaxy, the Andromeda Galaxy, which you probably all recognize from the background of most Macintosh computers. It's that nice, beautiful galaxy. It's like the canonical galaxy image. That's our nearest massive neighbor that's on par with the same kind of mass as what the Milky Way has. And then there are a number of small satellite galaxies or dwarf galaxies that are orbiting around one or the other or both, or kind of flying around. And yes, there have been some studies that indicate that there's some asymmetry there, and there's more galaxies over here than there are over here, or that there's kind of a disk-like structure. It's not entirely understood what the heck is going on, if this is just an earlier stage, and if as it becomes more stable, that you'll eventually have a more spherical distribution. It's just, it hasn't evolved long enough or something like that, but this is an active field where we're trying to understand what the heck is going on. That's not specifically what I work on, but it's related to what I work on. Does that answer? Okay. Other questions? And people who just came in, you're free to ask whatever questions you want. We'll do our best to answer them. Sometimes we do an okay job, sometimes maybe not so much, but we're free to take whatever you can throw at us.
Do we have any candidates for dark matter, like what they are? Like what are the leading theories of what it is?
So the question is, what candidates do we have for what dark matter actually is? So a little bit of history and background on this. So traditionally, so just as a background, dark matter, in case you don't know, is this thing that physicists have called into our theories because there's not enough visible material in the universe to hold the structures like galaxies together. We know that there's more mass there because gravity is holding them together, like our galaxies held together, but if you just count up all the things that we can see in electromagnetic radiation, like stars or even the accretion disks around black holes or planets, there's just not enough mass. And based on how quickly these galaxies are spinning or rotating, they would just fly apart if it were just that stuff holding them together. So to answer your question, the two main theories that people had for what actually dark matter was is something called, and they have these nice acronyms, machos and WIMPs. So machos stand for massive compact halo object, which basically refers to macroscopic scale things like black holes or planets or things that aren't necessarily exotic in terms of the physics, because a black hole or a planet, that those are normal things that behave physics as we understand them. They're just so dim that we can't see them with our telescope, something like that. And then the other alternative are WIMPs, which are weakly interacting massive particles. So these are the idea that dark matter consists of subatomic or individual particles that are, on par with protons or electrons, but much more massive, and only interact with other matter in terms of how gravity. They just don't interact with things with magnetic forces or other forces. And in general, machos are disfavored because there have been a number of studies looking for gravitational lensing effects. If you had, you'd have to have a lot of planets that we just can't see, or a lot of black holes that you just can't see. And we look for their gravitational influences in terms of lensing, how light gets bent around massive objects, and it just doesn't look like there's enough stuff like that in the outskirts of galaxies, or at least of our galaxy, to justify that. So in terms of WIMPs, this is an ongoing effort to try and either detect this when one of these particles, like perhaps slams into another one of those particles and releases radiation. So there are particle chambers for trying to detect this. Things like the Large Hadron Collider at CERN are actively trying to slam particles together in hopes that maybe we can do it at high enough energies that it can reveal a particular energy of the particle and mass of the particle. But it's definitely an ongoing effort.
It's like neutrinos, is that one of the things you're talking about?
Usually neutrinos aren't invoked because they're traveling too quickly and they're not massive enough. And so neutrinos, yes, do contain some significant amount of the energy and mass in galaxies, but they're moving basically at the speed of light, and so they'd fly away from the galaxy and not be able to contribute much to the overall bulk mass of the galaxy. They're considered too hot a particle.
Are there particles that are candidates? Have you know?
I don't know their names, but I don't know. Do you guys know? Do you have a better answer for this?
Yeah, so I do know a little bit about, in the particle physics side, there are some candidates. So like Cameron was talking about, the Large Hadron Collider at CERN is trying to smash together these particles and see can we try and recreate these WIMPs. And so so particle physics, there's this sort of standard model that, describes all the particles that we can see today. We have grouped them into classes like leptons, where electrons and neutrinos fall into that category, and then baryons, which are, protons and neutrons and things like that. So there's this beyond the standard model theory called SUSY, which stands for a supersymmetry theory, where every standard model particle, like an electron, a proton, whatever, has a supersymmetric particle pair. So you have, for every lepton, you have a slepton, which is the supersymmetric particle pair of that. So there are these sort of candidate dark matter particles in this supersymmetric theory called a neutralino. And so what they're trying to do at CERN is, CERN, they keep on trying to ramp up the kind of center of mass energy that they're conducting their experiments in the hope that they can, dig into new physics and try and recreate these sort of supersymmetric particles. So as of yet, the SUSY experiments have been unsuccessful. So the results are all null. They're unable to get a signal above the background noise that you detect. But yeah, this is just one, the kinds of things they're trying to do is they're trying to see if they can create these kinds of supersymmetric particles or non-supersymmetric particles called axions, or another type of name that gets thrown around. But yeah, there are a lot of beyond the standard model theories out there that invoke a candidate for dark matter.
Yeah, if dark matter only feels the force of gravity, how could you have dark matter halos? It seems to me that they would collapse a long time ago into the center of the galaxy or something like that.
So it is correct that when you look at a galaxy, it's surrounded by this halo of dark matter, but that halo is not just composed of dark matter. So that halo is actually pretty hot, and we call it a virialized structure, which means that there's basically like an equilibrium where there's still, because it's at a certain temperature and it's pretty hot, there's gas there that's in thermal equilibrium. So that's essentially, the competing force of gravity is balanced out by thermal pressure support in these dark matter halos because they're virialized structures. Cameron.
So they're held aloft. Okay, so let's just parameterize the dark matter as particles, which is usually what's done, as I said, in simulations. If you have a collection of particles and they're all traveling around the center of mass of the system, so they're traveling like this and like this and like this, there's no friction for these really to bring them down to the center. They're considered collisionless because gravity's the only thing that influences them. So they're just gonna, once they get on an orbit, they're just gonna stay on that orbit until something perturbs it from the outside or whatnot. But they'll just remain that way, and there's nothing that will be able to keep them and damp their trajectories to bring them down to the center where they'd collapse into a small structure.
Related to that, but so, outer edge stars in the galaxy rotate much faster than it should be. If the galaxy only has the matter that we have, so that's why you think that there's like 9 times more dark matter, right? But that has to be inside, because outside isn't going to affect things that are inside.
That's right.
So even though there's a halo of dark matter outside, there's got to be 10 times more dark matter than light matter inside also.
Yes, that's right. So there's definitely a radial profile where there's a lot more dark matter in the interior, and it falls off basically with an inverse square law. Yeah, but there's a lot of dark matter in the interior of a galaxy as well as in the exterior, but there's a lot more interior, and so that's what causes the acceleration of objects around it, because it just acts like a mass at the center.
I guess it just, like I said, since it only attracts gravitationally, nothing's going to, it's not going to lose energy. It's a tighter orbit, but it will still stay there forever, I guess.
That's right. There are some effects that will dampen the overall motion of very massive objects. There's something called dynamical friction, but it's essentially turning the bulk energy of a massive, like a satellite that's falling into the galaxy, into the energy. I mean, energy has to be conserved, so it increases the dynamical energy of the individual dark matter particles that are present. But yeah.
One other thing which is related, I also read that people are looking for gamma ray boosts caused by dark matter. I think that's what I read.
Yeah, so the question is, people, are there researchers looking for gamma ray bursts that are caused by dark matter? I think what you're referring to is, so obviously there's a lot about dark matter that we don't understand, but one of the proposals is that if these particles have some sort of self-interaction, where at high enough densities they have some cross-section for interaction between each other, or if you have a dark matter particle here and you have a dark matter particle here, that if they collide, that they could release energy and annihilate or something like that. And so the hope is to look at dense regions where there's a lot of dark matter, which is basically the centers of galaxies, specifically the centers of dwarf galaxies, and look for the signal of gamma rays, which wouldn't be produced by normal matter, particularly in the centers of these systems. So there's definitely efforts to try and find, I wouldn't call it a gamma ray burst, but gamma rays coming from these very, very dense regions where you might see a self-interaction of dark matter particles. That's right, yeah. Yeah.
So if dark matter were a ring, would that mean it also decay?
If dark matter were a WIMP, could it decay?
If it were like weakly interacting with it, that also causes it to decay?
Yeah, so going back to the experiments they're doing at CERN, so exactly what they're trying to do is like smash protons together, and that can form WIMPs, and then these WIMPs can then decay into other standard model particles that we can detect, because obviously dark matter, regardless of what kind of particle it is, we're not going to see the particle. So what do we see at CERN is the actual, visible decay products. Things like, neutrino, antineutrino pairs, and things like muons, antimuons, and stuff like that. And you can predict, what is the expected rate and number of these visible standard model particles that you would expect for a given, center of mass energy that you're operating your collider at, and rate at which protons are being smashed together, and so on. So, yeah, what we try and observe at CERN is like visible decay products from the decay of these WIMPs.
Yeah, so the question was, sorry, what? Oh, yeah. So the question was that I've written gamma ray bursts under my name, and what kind of data is being collected on gamma ray bursts. And so first, I guess, Nikita has reminded me to explain what a gamma ray burst is. We think that fundamentally what a gamma ray burst is it's a super, super bright flash of gamma rays that you pick up in your gamma ray satellite, right? But what causes these gamma ray bursts, we think that there are two different kinds. One is called a short gamma ray burst, a short hard gamma ray burst, and one's called a long soft gamma ray burst. The short hard gamma ray bursts are thought to be caused by the collision of two neutron stars. And when two neutron stars collide, you get these jets of particles that are moving at nearly the speed of light. And not only do you get jets, these jets aren't just like one smooth flow of material out. There's variability on like the millisecond level. So you might get one shell of material that is moving at half the speed of light, and then one shell of material that's moving at like 0.9 times the speed of light, and they're milliseconds apart. And so the 0.9, when it catches up to the half the speed of light shell, is going to collide into it, and that produces a shock. And that shock produces lots of gamma rays, and that's what you see as a gamma ray burst. And the other kind of gamma ray burst is a long hard gamma ray, a long soft gamma ray burst. And that's thought to be the collapse of extremely massive stars where something has managed to strip off the outer hydrogen and helium envelope of that star. And furthermore, whatever has done it has not been able to spin down the star. So you have to have a star that's rotating extremely rapidly and also have a stripped envelope. And when that star finally collapses and explodes as a supernova, it's thought that it forms a black hole at its center, and somehow that black hole taps into the rotational energy that existed in the star before and launches a jet. And you get a similar process where so short hard gamma ray bursts can last anywhere from like fractions of a second to like 2 seconds. Long soft gamma ray bursts last anywhere from like a few seconds to like thousands of seconds. And so, that to answer your question, that's one of the things that you can observe is the structure of the gamma ray light that's coming at you. Another thing that you can observe is the afterglow of the gamma ray burst. So this is the gamma rays only last for like anywhere from like less than a second to like a few thousand seconds, but the lower energy radiation, the X-rays, the ultraviolet, the infrared radiation, the visible light radiation, and finally the radio afterglow will last anywhere from sort of minutes to hours in the very high energy stuff like the X-rays to maybe like a few days, I think, in the visible. But the radio afterglow will last for quite a long time, at least weeks. Sometimes it'll last for years. And so you can learn a lot about gamma ray bursts by sort of studying across the electromagnetic spectrum the kind of light that you can get. Yeah.
Let's pose this question to Cameron on baryogenesis. What models describe the asymmetry in matter and antimatter so that we can be here today?
Oh, goodness. Okay. So the question is, what models do we have for baryogenesis, for the creation of like baryonic matter, like protons, electrons, and so on and so forth, versus the asymmetry of antimatter with antiparticles like antiprotons and positrons and so on and so forth? And I don't know the answer. I don't know. I put cosmology, but I don't do super early cosmology like that in the first, thousandth of a second after the Big Bang. Yeah, it's here.
So like from particle physics again, there are like these conditions that we know must exist in the early universe to create the universe that we know now. And, one of those is matter-antimatter asymmetry. I don't think there are any solid theories on how this asymmetry came about, but all we know for now is that it just had to exist, that there was just more matter than antimatter, so that when we had annihilation at some point, there was some matter that was left over to form all of the matter that we see today.
I had a question about different sizes of black holes.
Mm-hmm.
I've seen many times people at CERN say that because the black holes there are so small, they're a threat to humanity. And then so that made me feel pretty secure. And then I course, I know about the ones in space, but I was wondering, at what point does a black hole become dangerous in its size, or does it become dangerous for some other reason? And are there other cool sizes of black holes that you know of?
So yeah, I know there was quite a lot of concern when the CERN experiments first started up because of this possibility of creating these baby black holes. But again, they're destroyed as almost quickly as they were created, so they didn't really pose any sort of threat to humanity. And just going back again to my question of, stuff won't fall into a black hole unless it goes beyond the event horizon of that black hole, and that also depends on the mass of the black hole. So it scales with the mass, essentially. So the less massive it is, the smaller your event horizon is going to be. And also, just generally, I think there's a lot of crazy theories out there about how you can make black holes in the lab, but I don't think you really need to worry about ones that could potentially harm humanity.
Are all black holes the same density? So if you have two black holes that are the same size, would they be the same weight too? Or does the size vary?
So these black holes, they suck everything in, even light. And yes, they are incredibly dense. And because of that, their gravitational fields are so strong that they can even pull light in. But, we don't know anything about the internal structures of black holes, about the density distribution or anything like that. But, yep, as matter falls in and as black holes accrete, their mass does grow. So, yeah. Person in the back.
As a black hole is giving off mass from a black Hawking radiation, would it lose enough mass to a certain point where it's kind of reversed and it's no longer a black hole? Be a black hole when it has enough mass, but then lose mass to the point where it reverts back into a neutron star, or is it permanently a black hole?
So going back to how you form black holes, which is when you have, so the question was about Hawking radiation that can be emitted from black holes and whether that can, depending on the balance, can that lead to a black hole? Was it losing mass?
Losing enough mass to kind of reverse and go back to being a neutron star.
Yeah, so is it possible that it can reverse to go back to being a neutron star? So when massive stars collapse to form either a neutron star or a black hole, it's pretty much, it will either form a neutron star, and you can have processes where neutron stars can collide and then form a hypermassive neutron star that can collapse to a black hole, but you can't really get the reverse process of a black hole becoming a neutron star. Pretty much once you have something that collapses into a black hole, it stays a black hole. So I don't know much about Hawking radiation. Do you guys want to talk about it?
Sure, yeah. So for those of you who don't know, Hawking radiation is this process where you have sort of in these quantum theories, just in vacuum, you have these particles and these antiparticles that just appear out of nowhere. You just have some local concentration of energy, and then just randomly you get a particle and an antiparticle. And I believe the way that Hawking radiation works is that the antiparticle falls into the black hole and annihilates a little bit of the black hole, and that it loses mass. And then the particle flies out somehow. And that's about as much as I can explain of Hawking radiation. But I think to answer your question, for a black hole to turn back into something that doesn't have an event horizon would require, I believe, violating some sort of information thing or something like that. And also, black holes are much, much more dense than neutron stars. And so you'd have to sort of peel that material outwards, I suppose. And that's about as much as I know about this kind of stuff. Yeah. Mm-hmm.
I don't know if you guys can answer anything about magnetic fields or lasers, planets or stars.
Yeah, so the question's about magnetic fields in planets and stars?
So there's a really big... What?
I think the guy
Oh, okay. So I just want to preface, the question was, but what about magnetic fields? And I want to preface this question by saying that this is a really big kind of like inside joke in all of astronomy. Like anytime someone puts forth a new theory, someone in the audience raises their hand and says, but what about magnetic fields? So you just asked the most common question an astronomer could ask, so congratulations. But yeah, so magnetic fields are ubiquitous in all different parts of astronomy, and they play different roles depending on what type of object you're looking at, what size scale you're looking at. So I typically think about magnetic fields when I'm thinking about stars hiding planets. So stars have really intense magnetic fields caused by convection. So the plasma, or like the really hot, almost fluidy material in the guts of stars boils up and down just like water that's boiling. And this causes magnetic fields to be formed. And so we actually see, when we look on the sun, we can see dark areas on the surface of the sun called sunspots. And those sunspots form where magnetic field lines bunch up. And so there's a very, very strong magnetic fields on those sunspots. Do you have a follow-up question?
Maybe to further the question,
Sure.
What kind of research have you guys done on it, or like what have you guys found that is cool? Because I understand that part, but I just wanted to know, like, have you guys found something that might look at that, or is there something that's kind of crazy that is on the same as the planet, our planet versus the sun? I don't know, anything like fun stuff.
Okay. Okay, sorry. I was trying to get to the fun stuff. So the fun thing that I've worked on in particular is trying to disentangle what look like planets from what are actually planets. So sunspots, as the star rotates, stars have star spots just like the sun has sunspots. And those star spots can look like planets. Basically, they're very dense magnetic field concentrations, and so they suppress convection. So there's not material kind of flowing towards you in the way that there is on other parts of the star. So when we measure the radial velocity of the star, when we measure how the star is, how the star appears to be moving, this little bit of the star that's blocked by this magnetic field doesn't appear to be moving the same way that the rest of the star does. And we can falsely interpret this as there's a planet that's of this particular size that's tugging on this star. So if the sunspot stays for a long time, if it persists, we can falsely interpret that as a planet signal. So what I work on is using statistical techniques to separate the signals of magnetic field activity from actual planet signals. And yeah, it's possible, but you need a lot of statistics. Sorry, say that again.
Which do you think is more fun, discovering exoplanets or stars?
So the question is, what is more fun, discovering exoplanets or stars? You're talking to an exoplanet scientist, so I think exoplanets are really cool to discover. I think exoplanets are also really difficult to discover. We know about many fewer planets than we know about stars. Stars are bright; they emit their own light. Planets are dimmer. They're not undergoing nuclear fusion, so they're not creating quote unquote new energy that's being emitted. So yeah, it's really difficult to find exoplanets, which makes it really cool when you do find one. But there are also really cool types of stars out there that I'm sure are really fun to discover too. I don't know. What's one of your favorite things to discover? Curious.
I guess I'll first start off with a little bit about magnetic fields and planets. So I don't personally work on this, but my advisor does, and some of his students, or his former students do, which is, you may have heard that magnetic fields are very important in shielding planets from these solar flares, or these coronal mass ejections from stars. It turns out that when you have a solar wind interacting with a planetary magnetic field, that produces a kind of radio radiation called cyclotron radiation. And so there are active efforts to be able to detect planets using radio telescopes, which has never been done before. And so my advisor has built a instrument out in the Owens Valley Radio Observatory, east of the Sierra Nevada mountains up Highway 395. And basically it's this array that consists of like a few hundred sticks in the ground, like metal poles, basically, dipole antennas, that allows you to look at the entire sky, at least all the sky that isn't blocked by the Earth, all the time. And currently the only limitation to being able to just take a continuous video of the sky and the radio is the fact that you need incredible supercomputers to process all the data that's streaming in. I can't remember the exact statistic, but it's like, a non-insignificant fraction of all the internet traffic in the world would be like that data rate coming in from that telescope. And we simply don't have the computing bulk to be able to handle that data flow. But soon, one day, yeah.
So again, not something that I work directly on, but there is a cool role that magnetic fields can play in black holes. So the supermassive black holes I've been talking about can sometimes release very powerful jets. And a big area of open research is how do you produce such jets? What's the mechanism powering these jets? And so one really popular theory is that these supermassive black holes, often they're spinning, and they can spin pretty fast. So as these black holes are rotating, the magnetic fields that can be originating from these black holes can be wound up. And so these magnetic fields get wound up, and then particles at the base near the black hole can then be accelerated and launch this jet outwards as they are basically bound by the magnetic field lines winding around. And then you can then see the radiation that's given off as this jet then shocks the surrounding gas, the interstellar gas further out from the black hole. So yeah, black hole jets are really cool, and we think that magnetic fields that are wound up are what power them.
All right, it was just about when you mentioned studying binary white dwarfs. Observationally, I'm sure there's stuff we can learn about them. So what was that? And then, is the formation of binary white dwarfs any different than binaries of stars in the main sequence? Or then it made me think about neutron stars, because I thought you said binary. Someone mentioned binaries and neutron stars. So when it comes to binaries, is it just two things find each other eventually, or with white dwarfs, given that they had this history, is it different how they become binaries versus just stars, standard stars?
So how do you form, so I think the general question is, how do you form binary white dwarf systems? How are they different from stellar binary systems, and just generally about the populations of binaries? So a lot of the binary systems that we see, so white dwarfs are the kind of stars that you form at the end stages of life of, these sort of low mass type stars. So it's pretty common that these white dwarf binaries originated from stellar binaries. So, you originally had the system of two stars, and then those two stars just evolve over time, and then they reach their end stages of stellar evolution, and then you end up with the binary pair of white dwarfs.
But the ejection of all that matter doesn't interfere with them as binaries?
So binary evolution, there's actually a lot of kind of caveats that come in because you have two stars that are evolving next to each other that make it different from just single star evolution. So to actually model what happens in binary star evolution, the first input that you have is just regular vanilla stellar evolution. So you have two stars that are evolving next to each other. But you have to keep very close track of what's happening to those stars over their lifetimes. Because if they get stars, as they evolve, tend to get bigger. And as they get bigger, there's a higher probability that they'll interact. And there are lots of different ways that we think that stars can interact. And some really cool things happen when they do interact. So as an example, Certain types of white dwarfs we think can't actually be formed by regular stellar evolution. They have to be formed by binary star evolution. So one example of this is if two main sequence, so like solar type stars, are evolving very close to each other, and one gets really big and the other one is really close, it can kind of strip the envelope of the second one completely. So that one will never actually start helium burning. So it's a very, very low mass white dwarf that doesn't have any sort of heavier elements in the core. So those we think can only be formed by binary star evolution. With heavier stuff like neutrons,